Hello, welcome back. Today we're going to look at evaluating limits algebraically. And let's start off with a little review of the idea of direct substitution for evaluating limits that we talked about last time we were together. Essentially, we said that if a function is continuous, which means it has no breaks in an informal way to say it, if the function is continuous at a number a, where a would be a domain value, then the limit of f of x as x approaches a is f of a. And this meant for us that if we're trying to evaluate a limit problem, at a spot where a function is continuous, then we can just find the value of the function. Our simple way of describing this was plug it in. If we get a value, the function was continuous, and we've got our limit. So we'll be looking here in an algebraic setting at problems that do not have this property of continuity at a point, and what do we do about it? We're going to look ultimately at four kinds of problems. We're going to look at factoring problems. We're going to look at algebraic expansion problems. We're going to look at problems involving square roots. I'll just write radicals. And we're going to look at problems involving algebraic fractions. I'll call those rational functions or rational expressions. So let's start off with factoring problems, and we want to start with an important fact. Let's take an example like x plus 3 times x minus 4 over x minus 4. And if you're like most people, you're already thinking about canceling or dividing these factors of x minus 4. But here's an important fact. This expression on the left is not equivalent to the expression on the right. That statement is factual. To be not equivalent means every possible input value on the left and every possible input value on the right would produce the same output value. And we can see with a little bit of investigation that in fact those two statements are not equivalent, because over here on the left, x may not equal 4. If we tried to plug in 4 on the left, we get 0 over 0, and that has no value. But over here on the right, x equals 4 does produce a value. So this is important for us because while these expressions are not equal, it is also a fact to say that they are equivalent as long as we don't use 4 as an input value. But for every other value, those two expressions do produce the same output. So we can express this fact as they are equivalent for all values of x except 4. And that means when we come to a limit context, the limit of the expression on the left equals the limit of the expression on the right, in both cases as x approaches 4. Because remember, our definition for limit says we're looking at values getting closer and closer to 4, but never actually reaching 4. And so just the very definition of limit is already giving us this condition that x will not equal 4. And so for all other values, these are equivalent expressions, and therefore their limits are the same. So here's an example of how we're going to use this factoring strategy. Let's take for an example a problem like the limit as x approaches 2, x squared minus 6x plus 8 all over x minus 2. It's probably a good idea to get in the habit of trying to evaluate a limit just by plugging in the number 2. In other words, if the function that we're looking at happens to be continuous at 2, we'll get an answer straight away. This also builds in some routines that'll be helpful for us later. I notice when I plug in 2 to the denominator, I get 0. That's a red flag. When I plug in 2 to the numerator, I'm also getting 0. So those limit expressions that result in something like 0 over 0 give us information. They mean oftentimes we can do some algebra to find a limit value for this expression. So the factoring technique suggests that we factor the expressions. And in this particular case, the factorization for the numerator is x minus 4 times x minus 2. Now that's not a coincidence that we happened to get the same factor in the numerator and denominator. If we think about it, the factor theorem is the part that's giving us an algebraic value of 0, both the numerator and denominator, when we try to plug in 2. So this is sort of something we might almost expect in the 0 over 0 case. Now we can essentially equate this limit to an expression by what you might think of as canceling factors. And now we can evaluate this equivalent limit using the process of direct substitution. We plug in 4, and there's our limit value. Let's look at another example. In example 2, we're going to have an expression, the limit as x approaches negative 3. Let's use the cubic expression, x cubed plus 27, all over x squared minus 9. So it turns out that both the numerator and the denominator are factorable. Let's go ahead and give that a try. The denominator factors as a difference of squares, x minus 3 times x plus 3. And the numerator has a factorization too. You might need to pause and look up the factorization pattern for cubes, sums or differences of cubes. But I'm just going to go ahead and throw the result in there. That's x plus 3 times x squared minus 3x plus 9. Now in our work, we'll recognize that the same problem that we would end up with a 0 over 0 limit expression is coming from trying to evaluate x plus 3 at negative 3 in both terms of this expression. So essentially in our mind, we'll cancel those out. And the resulting expression should actually represent a function that's continuous when x equals negative 3. So we can evaluate this limit just with direct substitution. And plugging in negative 3 gives us 9 plus 9 plus 9 over negative 6. So we have 27 over negative 6, or in simplest form, that gives us negative 9 halves.